I will talk about something quite different now. I will talk about the role of dislocation, climb, and glide during creep. This is a classical problem. And creep takes place by a combination of glide and climb of dislocations, as many of you know. Weertman proposed that climb would be controlling if the stress exponent for the creep rate was about 5, but glide if the stress exponent was about 3. And some researchers are still considering this division. Most metals and alloys have in most cases a stress exponent of 5 and above at common creep temperatures of about half the melting temperature. However, there are some binary alloys where the stress exponent is about 3 in certain temperature and stress intervals. And the most investigated alloys are aluminium, magnesium, and aluminium zinc. At low temperatures and high stresses in the so-called power law breakdown regime, creep has traditionally been assumed to be glide control, simply because the diffusion is so slow that climb could not take place. New findings have, however, shown that these traditional facts can be questioned, and this will be the topic of my presentation. For life prediction models, it's absolutely essential to know if climb or glide is controlling, because the result is quite different. I can't move my slide. Oh, sorry. Okay, fine. Well, how does creep actually take place? Well, it occurs in the dislocation network. It consists of a number of dislocation links. And if the dislocation link is sufficiently large, it will be released by glide. It will move a long distance, and it creates new dislocation length. And this refers to work hardening because it increases the strength of the material. Thus, the average dislocation density is increased, and the dislocation link lengths are reduced, and new dislocation cannot be released anymore. So then there is a gradual coarsening of dislocation links by static recovery, and eventually there is a link length that is long enough to be released, and the whole process can be repeated. This is the basis of the creep recovery theory. The balance between work hardening and static recovery is crucial. This is the reason why we can have something like secondary creep, and that is actually the most characteristic feature of creep overall. There is a special class of alloys called class A alloys, which have this characteristic low stress exponent of 3, and aluminium, magnesium, and aluminium zinc, as I mentioned, are the most studied systems. And glide is then assumed to be the controlling mechanism, and there are some other features. There is no substructure present, and the primary creep can be different from the novel one. So the creep rate can increase during primary creep instead of be reduced. Now, these assumptions about glide control can be questioned. And the background is that in a dislocation-free alloy, the glide speed is very, very high. But in real materials, gliding dislocations cross other dislocations and they form jogs. And these have to move by climb, but they're moving much slower. So the glide speed is still much higher than the climb speed, but they are related. Another reason is that the activation energy for creep, even in class A materials, is close to that for self-diffusion, and that's indicating climb control. And again, this basic property of creep, that we have a balance between work hardening and static recovery, this means that we must have a recovery process even for glide control. And no such process is really known. Here we come to modeling of class A materials. And you can see it's for aluminium, magnesium, aluminium, zinc. We have the creep rate versus stress. And we can see this typical behavior that in a certain stress range, the stress exponent is 3. But at lower stresses and higher stresses, the stress exponent is higher. And in the classical models, it was assumed that we had climb here, glide here, and climb again. So there's a transition between different mechanisms. And that's always been quite difficult to explain. And we can see here for aluminium zinc that it looks much the same. This is a phenomena which appear at around 300 degrees C for these alloys. Now, the crucial question is here, can we have a static recovery process for glide? Well, the only potential mechanism is cross-slip, and this cross-slip is illustrated here. It means that the dislocations on one glide plane is moving to another glide plane. And for a split dislocation, it means that there have to be constrictions formed here to enable this movement. The width of the split is the width of the stacking fault, and I'll come back to that. Now, for a long time, it was quite uncertain what the activation energy for cross slips actually were. But I've collected quite a bit of data, and it turns out that the values can be grouped in 3 different categories. This is the top category, this is the second, and this is the third category. And the classical results can be found here at the top, and due to linear elasticity models, for example. More modern atomic simulations give results in the middle, but if you take into account the interaction with jogs and dislocation, you get even lower values. And the parameter on this axis is actually the width of the stacking fault, which was this width here. Now, for solid solution alloys, you can see here are the are some activation energy listed, and they are compared for cross-slip then. And they're compared with the experimental values for activation energies for creep. And you can see that the experimental activation for creep are typically much larger, and they are typically also close to the values for self-diffusion. So this is very difficult to combine with the idea of cross-slip. So cross-slip cannot really be a static recovery process. There's another uh, uh, situation also where glide has been considered, and that is at low temperature and high stresses. And this is usually referred to as power law breakdown. And you can see here for aluminium that at higher temperature, the stress exponent is about 4. You can't see that, but that's what it is. But if you go to room temperature, it's about 30, so it's much higher. And that is a characteristic situation. And initially, it was thought that it was impossible to explain the behavior at low temperature with climb because the diffusion was so slow. But in recent years, it's been shown that the straining can actually induce quite a lot of vacancies and increase the climb rate. And in fact, you can see here that this increase in the diffusion rate can be as high as 10 to 6 or even higher. So it's a very large effect. So it's no problem anymore to explain why climb can take place also during power law breakdown. Now, another feature is that creep curves at low and high temperatures look much the same. And here we see an ordinary stress time curve, strain time curve, and here secondary creep where stress, they look much the same, although the creep exponent here is quite high, about 50. But the simple conclusion is that as long as stationary creep is observed, we can be sure that creep is climb control. And I'll come to my conclusion. There are a number of reasons why it's difficult to assume that glide control is active, even for class A alloys. The transitions from climb to glide and then back to climb with increasing stress are difficult to explain. For example, there is no sign of solid breakaway, which has been one possible explanation. The creep rate versus stress can be well described by assuming climb control. I'd show that in the computations in the first slides. And I also mentioned that the activation energy for creep for solid solutions are close to those for self-diffusion, which is natural for climb control. So, in addition, cross-slip is difficult to consider for static recovery. Also, for power law breakdown, climb is the controlling mechanism. And the simple conclusion is that as soon as you get stationary creep, you have to assume that climb control is active. Some of the results are presented here are available in a publication, which is listed at the top here. If you want to know more about modeling mechanical properties without using adjustable parameters. These two documents are available. This is a paper and this is a book, and all of it is open access, so it can freely be downloaded. Thank you.